Hi, in this week's lecture, we will be covering Titrimetric and Chemical Analysis Part 1. There are many analysis methods that we will be covering in this module, but for this lecture, we will be looking at titrations and chemical methods. So first, we will review the basics of titration. We will be covering what is titrant and analyte, what are primary standards and standard solutions, what is equivalence point, what is an indicator, as well as what is a blank titration. The word titrimetric refers to titrations, whereas the word chemical refers to chemical reactions to identify a substance. So what is titration? You are very familiar with it. We have used it before in the lab, and it is very commonly used to determine the concentration of a known reactant. In pharmaceutical analysis, we commonly use titrations to assess the purity of active pharmaceutical ingredients or APIs, as well as excipients. This picture just shows how titration equipments have evolved over the years. Nowadays, this is how the titration apparatus looks like. The analyte, which is the thing that you want to assess or determine, is placed in a conical flask, and the burette containing the titrant is placed on top. So the titrant is a reagent that will react with the analyte, and you will determine how much of the titrant is used up to react with the analyte. The titrant is added dropwise, and the conical flask can either be swirled by hand or a magnetic stirrer can be used to stir it. In titration, these are some terms that you need to know, and we will be covering what they are in this section. Let's take a look at the setup in the diagram. The titrant is in the burette. You know the concentration of the titrant beforehand, and you are trying to find the volume that reacts with the analyte. After the titration, you will record the volume of the titrant used. The analyte is in the conical flask. It is measured out, for example, by pipetting 25 ml, so you are the one who determines the volume in the conical flask. The purpose of titration is to determine the quantity of analyte that is present in the sample. And this quantity of analyte can be calculated based on the volume of titrant required. So how do we ensure that the titrant concentration is accurate? We first need to standardize the titrant. To achieve high accuracy in titration, it is essential to know the exact concentration of the titrant. Thus, the titrant has to be standardized before use. We can standardize titrants by using primary standards. These are stable chemical compounds which are available in high purity. Our titrant, which is used to react with the analyte, are actually known as standard solutions. They are also called secondary standards because they are standardized by the primary standard. What is the difference between primary and secondary standards? Primary standards are available in very high purity. We also seldom use primary standards for titration. Instead, we use primary standards to prepare the standard solutions to be used in titration. For example, sodium hydroxide or NaOH tends to absorb moisture and carbon dioxide from the atmosphere, and this changes its concentration. Since NaOH solutions may not be very pure, the concentration of NaOH solution is determined by titrating it with potassium hydrogen phthalate, which is a primary standard. From there, the accurate concentration of NaOH can be determined. This is called standardization. The standardized NaOH solution, which is known as a standard solution or secondary standard, can then be used in titration with an analyte. Next, let's look at the term equivalence point. The equivalence point is the point in titration at which the amount of titrant that is added is just enough to completely react with the analyte solution. Sometimes there are multiple equivalence points. For example, when you have diprotic acids reacting with a base, so you can have two equivalence points in that case. Sometimes the equivalence point is also known as the endpoint. So how is the equivalence point or endpoint determined? We will use indicators, for example, pH indicators. These are chemical compounds that can change color when the pH changes, and this can be used to determine the endpoint or equivalence point of a titration for acid and base titration. There are many different indicators such as methyl orange, crystal violet, phenolphthalein. So which one do you choose? The correct indicator to choose will be the one that can change color at the equivalence point. Let's take a look at a few examples of how a suitable indicator is chosen. This first example is a titration of a strong acid with a strong base. The graph shows how the pH of the solution changes when more base is added. At the equivalence point, there is a sharp change in pH from about pH 4 to pH 10. So any acid-base indicator that changes color between pH 4 and pH 10 is suitable to detect the endpoint for this strong acid, strong base titration. Phenolphthalein, bromocresol green, or methyl orange can all be used. Just one drop of the added base will bring about a change in the color of the indicator. Next, let's look at the titration of a weak acid with a strong base. At equivalence point, the pH changes from around pH range of 7 to 10. Let's take a look at the three pH indicators and the pH range for their color change. The pH range for phenolphthalein to change color is within 7 to 10, so it is a suitable indicator. Bromocresol green and methyl orange change color outside of this pH range, so they are not suitable indicators. This pH curve for the strong acid weak base titration shows pH change from about pH 3 to 8 at the equivalence point. This time, phenolphthalein is not a suitable indicator, but methyl orange and bromocresol green are possible indicators. So, do we always need indicators for every titration? The answer is no. If the products change color when they are reacted, for example, potassium permanganate, then we do not need to add an extra indicator. We can also use potentiometric detectors to detect the change in pH at the endpoint. Potentiometric detectors will measure potential changes at the electrode, and this potential change is affected by the concentration of a particular ion in the solution. For example, a glass electrode that is sensitive to hydrogen ions can be used to detect pH change. One advantage of potentiometric detectors is that it avoids the issue of ambiguous endpoints where the color change of an indicator is not clear. Another advantage is that it allows for automatic titration using an automatic burette.